Okay, the stream is on. Okay, perfect. All right, I'll start recording as well. Okay. Okay, great. All right, let's get started. Thank you very much, everyone, for joining, and thank you in particular to Reza for taking the time. Also, we had to reschedule at some point, and I know it's pretty late in Singapore, so triple thanks to Reza for doing this. A really great pleasure to introduce him. Reza is a professor, he's an NUS Presidential Young Professor of Computer Science at NUS, National University of Singapore. And he's extremely well known for his work on privacy overall, but specifically in privacy machine learning, which is the topic of this seminar series. His work has received a number of awards from the S&P Test of Time Award, the Casper Boden Best Paper at PETS, and many other accolades. Really, his work is the proverbial seminal work when it comes to membership inference attacks in machine learning. And so today he's going to talk about advanced membership inference attacks. And so without further ado, thank you very much, Reza. Take it away.
Yeah, thank you very much. Thanks, Emiliano. This is a great pleasure. Thanks for having me. And hello, everyone. I hope all is going well. So today I'm going to talk about this problem of analyzing privacy risks of machine learning algorithms and the methods that we designed over multiple years as a community. And also the new thoughts and ideas that we have been working on recently here in my group, and notably Jiayuan, Adia, and Sasi, who worked on the recent developments in this domain. So when we talk about machine learning, right, usually we have this simple setting where there's a data set, there's an algorithm that trains a model on that algorithm, on that data set. And okay, so we are then concerned about the privacy of the model. But in a practical system, the system is more complicated than this. Usually we have multiple data sets, we train multiple models, data gets updated over time as we receive new data. The models get updated and fine-tuned. Afterwards, they might be deployed in the cloud as a service, or it would be deployed on people's devices and different machines. The model might get updated based on the data that they receive. The whole algorithm and the training could also be done in the cloud. And the data could come from one entity, or it could come from multiple entities in the setting of federated learning. And when you look at this whole ecosystem, there are so many different attack surfaces, or so many different ways that an adversary would be able to have access to the data or try to infer sensitive information about the data. So it is crucial in this complex ecosystem to have a way to reason about privacy risks. So I just want to clarify what privacy risks are. The simplest setting is where the adversary or the untrusted entity has access to the data, let's say during the training or during the inference time, the queries could be sensitive, of course, and also the training data could be sensitive. And we want to provide training or inference service while preserving the confidentiality of the data. The more subtle type of leakage is the indirect leakage, where the adversary does not have direct access to the training set, or in this case, but can observe the outcome of the training algorithm or outcome of the model, which is its predictions, and tries to go back and try to infer what was in the training set given the observables to the adversary, the parameters or the model predictions. So, of course, when we look at the model predictions, any user who's interacting with the model is learning new information, and that new information is ultimately due to the training data, right? So we are learning new information about the training data, and now the question is that a privacy violation, or is it a privacy violation if we learn any bit of information about the training data? Here we need to be more clear about what we mean by information leakage. So obviously what we want is that we want the user to learn something about the whole population, some patterns that apply to the whole population, but for protecting the privacy of the data records in the training set, we want to prevent an adversary to tell what specific patterns apply to individual data records in the training set. So we define leakage as information that an adversary could learn about the specific records in the training set, which he couldn't learn from the whole population, right? So what he learns beyond that is violation of data privacy. And actually this violation has been shown in practice on real world systems, right? So back in 2017, we showed that machine learning as a service platforms leak a ton of information about the data on which they train their models, and an adversary would be able to tell if a particular record is part of their training set by just having black box access to those models, because you have no access to the model parameters, you have no access to the intermediate steps of the computation, you might not even know what the training algorithm is. And but in practice, this is shown to be possible. And these kind of attacks could be expanded, and again, to another real world scenario where some large language models are trained on data and released. Now you have access to this, let's say, sequence to sequence model, and would be able to, using some reconstruction attacks, would be able to reconstruct partially the training data that could contain very sensitive information, right? Again, the adversary could run the same kind of attacks in the distributed setting as well. So if you are running a federated learning and where you allow different participants to share their model parameters repeatedly, and through some server, these parameters gets aggregated and sent back to the participants, the adversary, whether it's an untrusted aggregator or an untrusted participant of the network, would be able to see multiple snapshots, multiple updates from different clients, or aggregation of their snapshots, and try to run the same kind of attacks. And again, like in multiple papers, researchers have shown, including us, that the adversary would be able to reconstruct sensitive information about the training data of participants. So these are all the attacks that showed that actually all those attack surfaces that I mentioned and the potential vulnerabilities are being exploited on real systems. So there's a lot of focus on designing machine learning systems under some regulations that are secure against those privacy attacks and also other security attacks, right? So there are standards about this. There are some guidelines in the US, in Europe, in the UK, and the focus of all of these is basically to be able to quantify and audit the risk of machine learning algorithms with respect to data that is used in that pipeline, in the whole AI system, right? So, and also there is, of course, GDPR that mandates that we need to have some data protection impact assessment, a procedure to evaluate the privacy risk of any type of computation and process that we do on the data, so that we find the vulnerabilities and mitigate the risk of potential attacks, right? But the main question here is, okay, we know that the attacks are possible. We know that we want to design secure and privacy preserving systems. The question is how to audit privacy risk in ML, and what is the methodology, and what are the tools that we need to design that enable the auditors to audit complex machine learning algorithms. To answer that question, and answer that question in a systematic way, and enable ourselves to come up with a quantitative approach to measure privacy risk of ML, we need to design an indistinguishability game, which is the underlying game for differential privacy as well, although here I'm not going to talk about differential privacy. So there are two worlds that you can imagine. In one world, there's a data set, and then using that data set, we train a machine learning model, M. And in another parallel world, there could be a data set D union with some data record X as the training set, which could be used to train another model M prime, right? So in one world, the data set is D, which does not contain X, and we train a model. And in a parallel world, an alternative world, the training set is D plus X, and then we train a model M prime. The adversary is in one of these worlds, and the question is whether by making observations, which could be the model parameters or the predictions of the model, whether you would be able to tell the world he's in, right? And he would win if he's correct, right? And what does this mean? So if the adversary is able to tell correctly whether he's in the world where X is in the data set or the world where X is not in the data set, what it means is that the adversary is able to detect the influence of X on the model or on its observables. And it means that that algorithm, through that specific sample, which is the model, would leak information about an individual data record X. So if the adversary wins this indistinguishability game, and the success rate of adversary in that game reflects the information leakage of the model about its specific data records. So you can run this indistinguishability game for in an experiment where the algorithm, let's say, is fixed, the data set is fixed, and then there's some randomness maybe in the algorithm. So what you would observe is that sample from an algorithm that would produce a model. You can allow that experiment to include sampling different data points, right? So the whole process becomes sample some data from some population or underlying distribution, and then sample a model using a randomized algorithm. Let's say it could be a stochastic gradient descent algorithm or a noisy version of that, and then show the outcome of that to the adversary and see if the adversary could distinguish it with the parallel world where the data, let's say, is added to the training set. So you can try to run this game and quantify the success of the adversary across all possible combinations of the data sets and the models, and that is what differential privacy wants to make sure that the success rate of the adversary is bounded in that case, which is like in all parallel worlds that you create, the success rate of the adversary is bounded. But you can also have a specific scenario, right? So in any case, this is the game that we are dealing with to quantify the privacy risk of machine learning models or machine learning algorithms. And the way that we try to approach solving this game on behalf of the adversary is using membership inference attacks. So given a particular model or predictions of that model, we ask whether an adversary can infer if a particular data point was part of the training set. So the model is sampled, and a particular data point is also given, and then we're asking whether this is part of the training set of that. And this is a way to tell whether the adversary can distinguish between the two worlds. And we use the success of the attacker as a way to measure information leakage. Okay, so in the black box setting, where we only have access to the model predictions, we can query data to the model, get the prediction, and ask whether the data was part of the training set. So this field of research on membership inference attacks is has over the last let's say decade or so has been very active field of research. So there has been lots of very interesting papers on attacking released statistics about sensitive data, and also more recently on the privacy risk of machine learning models. And there are techniques that try to improve the accuracy of the attacker on some known data sets, or use machine learning, use membership inference attacks to estimate the true privacy loss through differentially private algorithms. And in all of these, we empirically try to measure the privacy risk and compare how things get better, or use membership inference attacks as a stepping stone to construct reconstruction attacks. So in a nutshell, in the context of machine learning algorithms, a membership inference attack, at least the early versions of that, would involve training a distinguisher for an adversary that, given the predictions from the model, would be able to recognize whether this prediction would come from the training data or from the test data, right? And empirically, again, we'll know that the statistical behavior of the model with respect to train and test data are different. For example, the model might be more uncertain on non-members and more certain on the members, larger loss value on non-members and smaller loss values on members. And after you learn this distinguisher, then you just test whether what you observe basically belongs to one of these two distributions. And by running those attacks, which showed to be very powerful, you could try to learn and ask this question of why machine learning models may leak so much information. And for example, we can just try to see if the attack accuracy is correlated with how overfitted the model is. And then you can see for different tasks with different number of classes, as the train and test accuracy increases, the attack accuracy also increases. So when the model is more overfitted, it would memorize more information about its training data and would leak more information about them. The information leakage about different training data is not uniform. It's not the same. And for example, if you have a small group or a small class, then the chance that the model memorizes information about the individual records in that small group is higher, and therefore the smaller the group is, the higher is the potential risk, and the higher is the attack precision. In the context of white box access to machine learning algorithms, you could see if you can run that attack and try to ask, okay, what are the characteristics of the models that would make the model more vulnerable to inference attacks? And we looked at pre-trained models, which are the most accurate models, let's say in 2019. And what we observed is that, for example, DenseNet, which has a large capacity but enables the model to be very accurate, has a very large test accuracy, is the one that has a very large privacy loss as well with respect to membership inference attacks when it comes to the case where the adversary has access to the model parameters. So basically, by increasing the capacity of the model, increasing the number of model parameters, it would enable the model, the algorithm, to search for more optimal model parameters, but at the same time, the model memorizes information, especially about the outliers in the data distribution. So we can move on, the same kind of attacks, if you run them on the context of federated learning, you can say, well, assume the adversary is the aggregator and is sitting there getting different snapshots of the model sent by the clients. And of course here, because the adversary observes multiple snapshots, not only can try to figure out what is member, what is non-member per snapshot, but also by comparing across different snapshots can see if the model behavior has changed with respect to, let's say, the loss or the gradient norm on specific data points, and that would increase the confidence of the attack on those data points. What makes this setting even more interesting and more vulnerable to membership inference attacks is that the adversary is able to also run active attacks, right? So inference attacks are usually passive, right? But in this context, the adversary would be able to influence what version of the model a client, a participant gets for the next round of training. And if the adversary can influence that, then might be able to influence the information leakage as well. And this is what we call the gradient ascent attack. Let's say the adversary wants to know whether a particular point Z is in the training set of a client. What the attacker can do is to try to increase the loss of the global model on that data point Z. And if the other clients has that data point Z in its training set, naturally, by using gradient descent algorithm, would change the model parameters to reduce the loss on that point, and this change would be detectable, and this would increase the attack accuracy. So all of these could be actually packaged in one particular, in one tool, which in particular we have done it for the tool that we call ML Privacy Meter. And this tool would enable researchers or practitioners to evaluate the privacy loss of machine learning algorithms in all these different settings: black box, white box, federated learning, and so on. So now the question that I'm asking is, okay, so far I talked about all the results that were out and the past results. The question I'm asking is that, can we do better in terms of formalizing membership inference attacks and also in terms of improving their performance and accuracy? Because membership inference attacks try to simulate that indistinguishability game that I mentioned before, but when you run the attacks, the accuracy of the attacks depends on so many different sources of uncertainty that the adversary has about which training data were selected, which algorithm is used, and the distribution of the data, and so on. So we want to formalize these things a little bit better understand the prior work, and also design something which is more accurate. So the rest of the talk would be about this paper that is going to be on archive in a couple of days. So you're the first one that I'm talking about publicly. And I skip the details and then the proofs and the references you can find in the paper when it's available. So to formalize the problem of membership inference attacks, we use hypothesis testing frameworks, where we have basically two worlds, right? As I mentioned before, the null hypothesis is the world in which a particular data point Z was not part of the training set of a model theta, and the alternative hypothesis is where Z actually was part of the training set, right? So if you want to simulate the world, from some population data, we sampled N records, and then we trained a model theta using a training algorithm T on that data set, and we sampled another data point Z from the population, and this would be the null hypothesis, where Z is not part of D. And the other setting, Z is sampled from the training set itself. So what we want to do is to be able to run a test that can tell us the difference between the two. So we can use the likelihood ratio test, where we compare the likelihood of the data Z and the observed model theta, or its predictions, under these two different hypotheses. And this could be approximated by e to the power of 1 over t loss of that data point with features x, z, and label y, z in the setting of a classification task. T here is a temperature for that model. And okay, so this is the likelihood ratio. And we need to have a test. Basically, based on this likelihood ratio, we need to define where we can reject the null hypothesis and what is that region. And this is done by comparing the likelihood ratio with a threshold, which effectively means that later on you would just compare the loss of the model on the target data point with some threshold. And so the attack would be that if the loss of the data points is less than a particular threshold, then we reject the hypothesis. But here, when we are running this test, we need to first define what is the false positive rate that we are going to tolerate, right? So the adversary would define specific false positive rate alpha. For that rate, it would find the threshold and then run the test with the hope that the true positive rate would be large for that given false positive rate, right? So this is basically the framework, right? So with some simplification and approximation, we have to do this comparison, compare the loss with some threshold. So now using this framework, I can explain how shadow model attacks work, right? So in the setting of shadow model attacks, where majority of the work in this field are based on that idea, more or less, or variations of that. The adversary tries to learn that threshold from the behavior of some shadow models that try to mimic the behavior of the target model, right? So you have some data from the population, you train some shadow models on those, and you know what data point is member and non-member of those shadow models. And then you learn the threshold from that, right? So in this setting that we have, in the framework that we have, you can learn that by computing, let's say, the loss of the test data of the shadow models on their corresponding shadow models. And you get a distribution of how shadow models behave with respect to their test data. And this is the histogram that you see here. And then you pick a particular alpha here. For example, I picked alpha equal to 0.1. And for alpha equal to 0.1, you have a threshold, which is how much of basically the mass here in this histogram is under that threshold, right? So that would be basically the false positive rate, right? Because we know that in this histogram, all of this data are test data of the corresponding shadow models, right? So whatever we say on the and falls on the left side of this threshold, the black line, would be false positive, right? We infer member while we know that it's not member, right? So we are going to tolerate this much error, and then let's say there's a data point which is a member, and with the red line would indicate the loss of that data point Z1 on the model given θ1. I'm just asked, okay, if the loss is less than that threshold, then predict member, right? So for this particular sample that I'm illustrating, the attack fails because the loss of this member is larger than the threshold. So the attacker fails to detect that. But this is how the attack works. The question that I'm asking is, can we do the same attack more efficiently, right? Instead of training multiple shadow models and try to learn the distinguisher or the threshold in this likelihood ratio test from those shadow models that requires training so many models, can I do it faster, right? And get more or less the same accuracy, for the attack, or perhaps even better. I skipped the how we derive this, but the way that you can run the attack is to see how the target model behaves with respect to the population data. And with high probability, the data that you sample from the population is not going to be a member of the target model, member of the training set of the target model. So the distribution that you see here, the green histogram, would reflect the loss distribution of the target model on most of its test data, right? So if this is the distribution of the loss of the target model on its test data, then I can ask, well, you know, if the loss is smaller than some threshold, then it's going to be in the training set, because it does not belong to the green distribution, right? And as you can see, these two histograms are more or less the same. The histogram, the green and the blue one underneath, is the same. And it indicates that this attack, basically the shadow model attack, tries to estimate this by running exactly the same attack on shadow models, right? So we don't have to train shadow models. We don't have to spend so much time on that. And by just having samples from the population that you use to train the shadow models and query the target model, you would be able to get the same distribution, which is the likelihood ratio under the null hypothesis. Under the threshold, you reject it. So again, for this particular sample that we picked, the theta 1 Z1, still the threshold is smaller than the loss of the data point, and the attacker fails to detect that this point is a member. So what I want to elaborate on a little bit here is that there are some uncertainties that the adversary has in running this attack, which is, well, what exactly is the distribution of the test data on this model, and what exactly this has to do with the target data that I'm attacking, right? What I want to highlight that the attack using shadow models is completely independent. The threshold that you learn is completely independent of what model you want to attack later on and what data you want to attack later on, right? So what are the features of the data that you're attacking? And what is the model that you're attacking? What is that theta? They don't influence the thresholds that you use for the likelihood ratio test. So there is some inherent uncertainty in constructing that attack, which is, I don't know what model I want to attack. I don't know what data I want to attack. Overall, I know that the behavior of models with respect to their test data is like this, and I'm going to use that and leverage that to figure out whether a data point with a particular prediction is a member or non-member. So hope that this is clear, that shadow models are global kind of attacks. They're not attacking a particular model, right? So when you design them, when we go to the population data attacks, the attack depends on the model that you're attacking, depends on the target model, right? Because the threshold is computed based on the predictions of the target model on some population data. So this has to be less uncertain because it knows what model is under attack, right? So, but what it's missing is that the threshold is not designed based on what data point I'm attacking, right? Still, that piece of information is missing, and the adversary's uncertainty about that could be the reason why the attack still makes lots of errors, right? And as you can see in the distribution, depicted as this histogram, the histogram is pretty large, right? And therefore, so many data points with different loss values might fall on the right side of the threshold. So let me just compare the two attacks that I just talked about, the shadow model attacks and also the population data attacks. And as here, what I want to see is that show that look at the x-axis, and that is the difference between the threshold and the loss when you run the shadow models, right? So when the difference is positive, when we are on the x positive side, the shadow model attack is correct on detecting members, right? When we are on the negative x, the shadow model attack is wrong, cannot detect members, right? So in this particular case that I'm showing, maybe the attack accuracy is about like 50, about 60%, because on the shadow model attack, because 60% of the points fall on the right side. Every point here is one single data point that I'm attacking. And if you look at the y-axis is the performance of the attack based on population data. The positive y is when the attack is correct in detecting members and as members, and the negative one is where the attacker misses members and makes an error. So the attack accuracy for the population, by just looking at the positive y, is about maybe 61%, right? So slightly better, more accurate than the shadow model attacks. But as you can see that they are very correlated with each other, right? So most of the ones that this one detects correctly, the other one also detects, and the difference between the threshold and the loss, the red line and the black line in the previous figures on the attack S is very correlated with attack B. So effectively, attack S, the shadow models try to approximate attack B. So this is observation number one. But attack B does exactly the same thing in a much faster way, right? You just get some population data, query the model with that population data, construct the histogram, run the membership first attack. So, but still, I'm not satisfied with the accuracy of these attacks, specifically because I know that for the population data attack, the attack is not dependent on what data points we are attacking. And we know that when we talk about memorization behavior of the model, we are talking about specific data points, right? We are talking about whether the model has memorized this particular data point or not, right? In the indistinguishability game that we talked about, we're talking about whether behavior of model with respect to this particular point is different or not. So what we do is that we design the attack, which actually a couple of other papers have some variations of this, but here we represent it in this framework, is that look at the shadow models that we trained before, right? So we call them reference models here because we are not going to use them as a way to approximate the target model. We're going to use them as samples from models trained on the population, right? And see how the behavior of the target model on the target data point is different from the behavior of the random samples of the models from the population, which are the reference models on the same target data point. So here, the attack algorithm depends on exact target data point that we are attacking, right? So what we are asking is that how much is the loss of this point on the target model, and how much is the loss of that data point on some reference models? If the loss of the data point intuitively on the target model is smaller than, let's say, the loss of the same data point on some reference models that do not contain this point as their member, that's a good signal that this could be a member of the target data point, right? So that's the intuitive idea. So what we do is that we just look at the loss distribution of the target data points on the reference models, and this is the new histogram that you see. As you see, it's more concentrated. The adversary has less uncertainty about non-members, right? So because this target data points is a non-member for all the reference models, right? And then we just get the loss distribution of that point on that reference model. So the threshold, again, for the same alpha 0.1 is the black line, and the same data point that we were attacking using the previous attacks, this time falls on the left side of the threshold, so the attack is able to actually detect this accurately, and it is a member, it is detected as member, and the attack does not make an error. So this is very interesting. One observation or something that I want to highlight here is that, again, going back to the notion of memorization, the question is that if I add these data points to the training set of a model, how much the loss of that data point would change, right? Would it force the model to memorize it? Or is it just a typical data point, and whether you are there or you're not there, the model behavior would be the same, right? If it's going to change the behavior of the model, then that would be recognized when we compare the loss with some reference models, right? So effectively here, what we are doing is that we are testing for memorization of that data point. But what I want to highlight that the attack construction, though it depends on the data point, it does not depend on the target model, right? So here the threshold is learned by querying the target data on reference models. I ignore the target model. So as you may expect, so the question that I'm asking is that, can we do the same attack, perform the same attack even more accurately, right? So we constructed this attack, which is more complex computationally than the one that was based on population data, but it's less uncertain and potentially has a better true positive rate for the same false positive rate. So to remove even more uncertainty, what we want to do is to just say, well, let's remind ourselves what the indistinguishability game was. The indistinguishability game is effectively something that you can call the leave one out attack, where you have a data set with a data point Z, and you just remove Z, and you have the rest of the data, and then you train a model on it, right? So you have the model with Z, the data with Z, and the data without Z, but the rest of the data is exactly the same. And we wanted to distinguish between these two, and we want to get as close as possible to that attack, because otherwise the adversary has still some uncertainty about what would be the effect of some other data in the training set on the loss of this model, right? As I mentioned, you could be an outlier with respect to the rest of the data, and therefore the model has to memorize it. What if the rest of the data is around this point and doesn't make it an outlier, right? So these are different scenarios. The adversary should be able to distinguish them. So we want to remove the effect of the uncertainty of the adversary due to the effect of the rest of the data set on the attack. Because the adversary does not know them, right? It cannot run the leave one out attack. So how do we do this? The intuition is this for this new attack. And this is a totally new attack. The population data attack, I would say, is based on some Homer et al. Attack. It was not designed for ML, but we could reformulate it here. The shadow-based attack is the one that most of the attacks are variations of it. Reference-based reference models attack is something that there are a couple of papers on that. But this is a totally new attack. This is based on the idea of having reference models. But what I want is that I want the reference model to be as close as possible to the model which is trained on the training set of the target model, excluding Z, right? How do I get that? How do I construct that reference model which is very close to the leave one out trained model? The main idea that we have is that we want to actually maximize the agreement of that reference model with the target model on all the data except the target data that we are attacking. And we achieve this using distillation. So you have some data, you distill the target model through that data, you construct your reference models. And in this case, the reference models are as close as possible to the target model, but because during distillation you don't touch the target data, then that remains the uncertainty that the attacker needs to test. So with this idea of distillation, or trying to replicate the leave one out attack as accurately as possible, we construct an attack that depends on both the target data and the target model. Basically, the threshold that you construct is model dependent and data dependent and has minimum uncertainty about the other factors of uncertainty, except the leakage, right? So at least compared to the other attacks. So here, again, what you do is that you construct these distilled models and you run the attack similar to the reference models. You compute the loss of the target data on all the distilled models. You get a distribution. There's this red histogram. And then you just compute the threshold and then you run the attack. And as you see the histogram, the distribution of the loss under the null hypothesis is even more concentrated compared to the reference model attacks, right? So the adversary is even more certain that for this particular target model and target data that I'm attacking, what is the test data distribution, right? And runs the attack based on that. So as I want to show you here, again, I compare the reference models.
Sorry to interrupt. So we're kind of running out of time. So if you could sort of start wrapping up, it would be great. So we have some time for question. If you can. Thanks.
Sure, yeah. I'm almost done. So let me compare the agreement between the distillation-based attack and also the reference model attacks, because they are very similar to each other. Again, on the x-axis, you have the performance of the reference models, and on the y-axis, you have the distillation models. There's a lot of agreements, but you see that the data is shifted towards the positive y. So the distillation attacks or showing more accuracy in detecting actually the members. So here is the animation of the whole thing. We had this attack, then the distribution changed. We had a better attack using reference models, and even a better attack using the distillation models. And the confidence of the attack increased. The attack also, at least for this particular data point, doesn't make a mistake. And what you are interested in when you are analyzing the privacy risk of a model for this likelihood ratio test is, okay, what is the true positive rate that you get for a particular false positive rate, right? So for when we get to the smaller false positive rates, you will see that actually these new attack based on distillation performs much better, and overall the area under the curve is much larger for this attack compared to the other attacks. So basically, to conclude, machine learning is vulnerable to inference attacks. We have discovered some attacks, and in the future, people might come up with some more attacks. So what we need is a set of tools and systematic mechanisms to audit these algorithms. And membership inference attacks are designed exactly to capture the information leakage. It's a generic way to evaluate privacy loss, and it could be standardized for this particular purpose. But the algorithm needs to be designed to actually capture that information leakage, which is the target of this auditing, right? Otherwise, the performance of the attack would depend on some other uncertainties that has little to do with the information leakage, right? So we want to design something that actually captures exactly the membership and nothing else. And okay, so I presented a framework in which I can explain different attacks, and also I can come up with new attacks where you can read the details in the paper in a couple of days. And there is, of course, the ML Privacy Meter tool, which is an open source tool that implements these algorithms, and then you can contribute to it or use it as researcher or practitioners to evaluate privacy risk of models that you train. With that, I'm done, and yeah, happy to take questions.
Great, thank you very much, Reza. Thanks a lot. I'm going to read one question of the YouTube chat before stopping the stream. So Adam has a question. It says, to prevent the potential privacy leakage, for instance, memorization of the model, we can maybe use DPSGD. Right? However, instead of perturbing all weights with differentially private noise, I think it'd be more effective if we can selectively perturb a specific subset of weights that is especially related to private information. So he's wondering if this is a valid thought.
Look, any kind of obfuscation and randomization that you do is going to somehow hide some type of information, right? All the question is, can you reason about how much protection that brings, right? That's the idea. So I don't know. You might be able to prove something or use these tools to evaluate the privacy risk of those algorithms. But one thing is that I want to highlight is that privacy auditing or security auditing is not a proof for privacy. It's rather tries to find evidence for lack of privacy, right? So you can try to attack it, and if the attack works, then you know that your method is not privacy preserving.
Yeah. Okay, thank you very much.